Good afternoon, everyone. So, let me ask one thing first. How is your assignment coming up? Is it coming up smoothly? I think day after tomorrow, I'm going to expect your assignments. Okay. Please make sure that all of you share your videos. So, not only you have to share with me, you have to share it with the whole class because whatever is being discussed in those presentations are pretty much in your syllabus as well. So from all the groups with what are being discussed. Okay? So expect them to be also in your syllabus. So make sure that you share it with me as well as you share it with everyone in the class. Okay. So do you have any questions so far on wells? Anyone any question about wells? So we have discussed different aspects of wells so far. Anyone having any doubts? Okay. If not, then let's begin the discussion. And today we are going to look into seismic interpretation. Now, for fourth year and fifth year, I have already in your geophysics class, I have already talked about seismic a lot. So, and also for third year in your solid earth geophysics class, I will talk about seismic with greater details. But in this particular course, we will primarily focus on the interpretation part. So we will not discuss a lot about the basics of seismic, how the wave propagates and everything. That I will cover mostly in the solid earth geophysics. Here I will talk mostly on the seismic interpretation part. And why do we need to take the help of seismic technology? That is something I had explained before, but let me try to do that once more. Suppose uh, this is the surface of the earth. Okay, this is the surface of the earth, and then of course the subsurface which you cannot see. Okay, that is where within the rocks, within the porous and permeable space of the rocks, your oil and gas is situated, right? So this is which is absolutely you cannot see. Now by drilling wells, okay, which are nothing but few hairline informations. So in these places you have drilled perhaps wells, okay, and you get very high resolution information, of course, but they are hairline information, okay. But then these well informations will not be enough to actually understand how the subsurface looks like. Okay, so we will not be able to know whether there is a structure developed, whether there is a fault, there are faults, how the sediment bed thicknesses are, and everything, because these wells will not provide us a very good three-dimensional picture of the reservoir. Okay, and hence you take the help of seismic interpretation. Okay, and what you essentially do in seismic interpretation is you send acoustic wave, and the acoustic waves are actually reflected back. Okay, and from the reflected back waves, okay, you kind of generate acoustic images, and those images essentially help you to identify subsurface structure. Okay, let me start this lecture by showing you a small YouTube video, and then we will get into the actual discussion. Okay. So you can see, if we, from a very primitive thing, for example, when we speak itself, it creates vibration, right? So fundamentally, creating acoustic signals starts with creating, when we speak. Okay, and then when these particular vibrations essentially meets resistance, or on the other hand, it changes its media. Okay, so this was traveling through one media, and then it comes to another media. What happens? Some part of the wave, it essentially reflects back. Okay, okay, and this is what we call as echo. Okay, and similarly, for example, this technique is used by bats whose eyesight is not very strong. So what they do, they essentially send acoustic signals, and then those acoustic signals essentially come back. Okay, and then, I mean, the sound waves that comes back, and they can essentially identify mm, an object which could stop its way. Okay, and then, for example, about ultrasounds, so something that you can't see, for example, this fetus inside the mom's womb, you can't see it from the outside, but you can check the health of this fetus by the help of ultrasound. So what it does, it actually essentially sends ultrasound signals, sound waves, and that sound waves essentially comes back, reflects back, and from those reflections, it is actually convoluted to some sort of picture, and that picture provides you an information which you cannot see, right? Okay. So seismic essentially works in the same way. In case of ultrasound, of course, people send ultrasound. I mean, this is ultrasonic sound. Okay, the frequency is really, really high. But then, of course, for for seismic technologies, the sound waves have lower frequencies and higher wavelength, of course. Okay, so similarly, for seismic technology, we are creating such sound images by sending signals, right? So you can see here, this is where seismic acquisition is taking place in the sea, in the offshore. Okay, so this is a vessel where seismic acquisition will take place. Okay, so it has two components. One is a source. From the source, it actually creates continuous vibration, and that vibration essentially creates sound waves. Okay, and then it also has receptors. Okay, that will be clear in a moment. Okay, you can see here, this is the vessel which is moving, and this is the source from where it is actually creating sound waves. And then with this trail, which is actually called fish, okay, with this trail there are receptors where the sound wave will be essentially received, right? So you can see here. So this is the water, and this is the bottom of the sea, and here the sound wave is being generated, and the sound wave is propagating. This is what we call these spherical things are called wave fronts, as you know, and these are called wave paths, right? The perpendicular lines uh, to the wave front is called wave paths. We will discuss in detail about wave fronts, wave paths, and so on and so forth for third year in your geophysics class. But I presume fourth year and fifth year actually remembers these things. Okay, and then you know the sound wave is going down, and then depending on the frequency of the sound wave being sent, that gets essentially, when it touches different lithologies, it gets reflected back, and the reflection characteristics will depend on what type of boundary it is actually reflecting against, whether it is reflecting from sandstone to shell, or shell to sandstone, and so on and so forth, whether it is getting reflected by something where there is water, whether it is getting reflected by something which has hydrocarbon. Okay, and then it is being reflected, as you can see. Okay, and then of course it is being received by these receptors, right? These are called seismometers, where they are received, right? These microphones or the seismometers are actually evenly spaced, as you can see, to get a good normalized picture. Okay, similarly, in land, you can see here there is like a, this is actually literally called a hammer. There is some hammering going on, and these hammers, I mean, pretty heavy hammer for that matter, it is being carried out by a truck. And while this hammering is going on, it is creating sound wave. Okay, and then the sound wave is essentially propagating through the inside of the earth, and then it is being reflected. Okay, and then finally it is also being received by different seismometers, and then of course this is nowadays is received digitally, and then is being, and such information is being processed. We will discuss about the processing part in detail in your um, the geophysics, but the processing is already known to the other two batches. And then, of course, yeah, so you can go all the way up to 10 kilometers with this technique to get an image of the subsurface. Okay. And then this data, whatever you have acquired, is kind of processed. Okay. And an image of the subsurface, a 3D image of the subsurface is generated. Okay. Then, of course, this is done by a geophysicist. Then the geophysicist interacts with the geologist to come up with a proper geological solution of how the thing actually looks like. And then they try to identify the different types of traps, reservoirs, source rock, and then, of course, what type of fluid that it might have. Okay. So, any questions so far? Anyone? Was that video clear for you? Can someone just say yes or no? All right. So let's get into the actual seismic interpretation part. So this is what I have been telling you, that this is an offshore. The picture that I'm showing you right now is the picture of an offshore acquisition system. Okay. Let it go to the presentation mode. So this is a picture of the seismic acquisition mode, and you can see in the offshore, of course, and you can see this is my which what I just explained before. This is my source. Okay. This is my source S, and then of course these are my receptors. Let us write them as R1, R2, R3, Rn. Okay, so on and so forth. Of course, then the sound wave. This is what we said. This is what we call as wave front. This spherical stuff we call as wave front, and these are called ray paths. Okay, and then of course, as you can see, in for example here, this in all the layers, it gets, some of it is reflected, some of it is actually transmitted back, transmitted deep inside, some of it is also refracted, right? And then you can, I mean, when it will reflect, when it will refract, will depend on something which we called as acoustic impedance, which is a product of rho and v, rho being the density of the layer and v being the velocity of the sound wave through it. Okay, so so a particular ray will only reflect, if there is a contrast in, so this is rho 1 v1. Suppose this is the acoustic impedance of the first layer, then this is rho 2 p2, this is rho 3 p3, and so on and so forth. So if the contrast is large enough, only then it actually reflects. I mean, sufficient energy of it is actually reflect. And once it is received by these receptors, then there is once it is received by the once it is received. Sure. Yeah. Once it is received by the receptors, it is actually processed. And you can see in this particular cartoon what I essentially was discussing is the product between the velocity and the density is called acoustic impedance, and the contrast in acoustic impedance is actually determines how much energy will be reflected, right? Now, so this is a real picture of a seismic vessel. Okay, you can see here in this seismic vessel, here is a small helipad. Okay, the helicopter can get down here. Okay. And of course, there is a source somewhere here. Here is my source, and these are all my receptors. Okay, these are all my receptors. All my these yellow stuffs are my receptors. So what it does, so suppose this is the area perhaps we want to essentially investigate. So this seismic vessel does like something like this. It goes in one direction, then it goes the other direction, like this it does. Okay, and while going like this, it covers the entire area. So, and after this is done, they do a perpendicular traverse. Okay, so once one says, suppose if this is called, this is east west, this is north south. Okay, so they first do an east west traverse, and then they do a north south traverse. So maybe the east west traverse will be called inlines, and the north south traverse will be called cross lines. Okay. So now what I'm seeing, that for example, that I am having data. Okay, I am having data on these individual inlines, okay, and cross lines, right? Now, if I just pick up one individual inline or cross line, this data is 2D, two-dimensional data. Yeah, because simply it will provide you one cross section, okay, one cross section of the subsurface. Okay, if you essentially process that data. So one cross section, two cross section, three, four, and then one, two, three, four, five. Okay, so they are like cross cuts or cross sections of the subsurface, but this is still not 3D. So what you can do to actually fill up this data gap, this is my data gap, of course. Yeah. So you can use different, high power computing and algorithms to actually do interpolation. Okay? Interpolation where I don't have any data. So if I do interpolation, what I will essentially, from this 2D survey, what I will come up with essentially is a 3D volume, right? 3D volume where essentially everywhere I have data. So there is no data gap. This is what we call as 3D seismic. So 2D seismic is nothing but seismics which are shot on individual lines. Okay, it could be an inline, it could be a cross line, depends on essentially the stretch of the field, and then you can interpolate that data to cover um, the missing data, and then you can create a 3D volume. Then there is also something called 4D seismic. There is also something called 4D seismic. What is 4D seismic? Suppose, for example, I capture a 3D seismic at, one 3D seismic, okay, maybe at 1990. And then in 1990, I start producing from that field, okay. And then, for example, after in 2020, I take another 3D seismic over the same field. Okay, so I might observe some characters of the seismic is being changed simply because it has been gone through a lot of production. I mean, a lot of hydrocarbon has come out already. So there might be some change in the seismic character. So when we study these time series seismic between two time intervals, one taken at a pre-production area and maybe one taken at a post-production time, and then we study the difference. This is what we call as 4D seismic. Okay, once these are taken in different intervals. So I hope I could make you understand what is 2D seismic, what is 3D seismic, and what is 4D seismic. And this is I will, as I said, I will discuss about the details of seismic interpretation. Sorry, seismic acquisition and processing in near geophysics class. I'll just give you a brief, so you can see here. So I have, for example, you know, uh, suppose this is source. Let me see. Suppose this is source. This is receptor one, and suppose this is receptor two. Okay. Now I will be able to image. I will be able to image this particular boundary. Yeah, here the boundary is between water and sediment, and these boundaries are, by the way, called as reflectors. Okay, in seismic we call them as reflectors. Okay? So I will be able to image them between this source reservoir pair, and I will also be able to image them with source R1 pair and source R2 pair. I will be able to image them with both of them. Okay. In the first one, I will observe, because for this, if you try to understand, so what I essentially would have to do, that the seismic wave has to come from the source, get reflected at this interval, and then go to 1. Okay. Similarly, it has to come from the source, travel through it, and go to R2. Right. So for the first one, it will take more time. It will take less time. Suppose it will take T1, and then this will take more time, T2. Okay. So now if I essentially plot time against distance, I will be able to actually catch this particular reflector twice. Okay. One with source SR1 and similarly to SR2. Okay, at a particular time interval. Okay. And then we can essentially change the position of the source. I can go to a separate position of the source now, because this thing is moving. Okay. And then I can keep on repeating the thing. Okay. Once I keep on repeating the thing, I will be able to actually, you know, understand the position of the reflector with respect to the with respect to the ground surface, with respect to the mean sea level. Okay. I'll be able to understand the position of the reflector, and then this is how, if you repeat that over a great amount of area, and then you process the data with if you process the data um, with some software, you should be able to actually create seismic images. Okay, how this process is done, I know it's not very clear for at least third year, but we will discuss that one with greater details in your geophysics class. For the time being, remember, this is the basic philosophy by which seismic acquisition is done, and then there is a large process of seismic processing, and after the processing is done, we actually come up with these sort of images. Okay? So this is nothing but this is a 2D seismic line. Okay, this is a 2D seismic line. Okay, that means if I think of this is my ground surface, okay, I am just having one cross section. Okay, that is what I am looking at, and these are all different. So these colored stuff, these colored lines are nothing but these are all different reflectors. Okay. Now, if you look at this set of reflectors, and I tell you this is the image of the subsurface, what does come to your mind? Let me ask from third year itself, okay, because I hope fourth year and fifth year can answer it already. So anyone from third year, please unmute and tell me what do you see here? Anyone, please. Come on. Anyone? Then I have to pick up people. Okay, Nirul, tell me what do you see here? Hello, am I audible? Nirul left the meeting. Okay, let me ask Jitendra. Jitendra, what do you see here? Jitendra sees holds. Okay. Yeah, I mean, if you unmute and speak, that is better for me. Otherwise, it becomes difficult to look through the chat. Okay. Yeah, if you please unmute and speak, that will be better. I ask a question. Let's get on with it. Of course, we will get into the fold, but you can see something. Of course, you can see like at the very top, up to this, I can see more or less, straight reflectors, right? So straight reflectors means horizontal beds. Okay, these are perhaps my horizontal beds. Okay. And then I can see there is a small break. The deep actually changes. So what it means, perhaps we are essentially, this break could be anything, but most likely this is perhaps a shelf break. That is, we are coming from the onshore to the offshore. Okay. Another important thing that you observe, that this package and this package, if I look at here, so if I call this A and this B, I see that the B is kind of folded as as you pointed out, but A is kind of horizontal, right? So perhaps the interface between A and B is an unconformity. And of course, I can observe these beautiful folds here, okay? Of course, these folds are here as well. So these are my synclines. This is a syncline, and then I have corresponding anticlines as well. Beautiful. So within this, we also you can see that here perhaps there is strong reflection coming up, and then here the reflection is little bit lower. So perhaps the quality of the sedimentary rocks is actually changing across this horizon, and so is here. So something is changing with respect to the sedimentary. What it is changing, we cannot essentially tell you. But if I have had a well here, okay, perhaps if I have had a well here, and at that depth, perhaps if I had found a shell here, okay, then I know this layer which is kind of continuous, everything here is shell. So what I tried to say that perhaps I have a well here, okay, and then while I encountered, that well, and from my gamma ray log, I found out that this is shell. But I know that shell is only here, I mean only this part. But then by correlating my well with the seismic, I can actually say that the shell layer kind of continues all the way here, all the way here, right? Hmm. Now, if I ask you, where do you expect the oil and gas to actually be? Okay. And the oil and gas would be, so if I want ask you to identify the trap, so the trap is perhaps here, right? In this anticline, in the anticline. And how far will it be? How far will it stay? It will stay up to this, because we discussed before that this will be then my fill point. Yeah, because after this point, this will kind of go away from the area, and maybe also I can also have hydrocarbon here till the spill point. Same is so is here till the spill point. Okay, provided these are actually guided by, these are provided you know there are shells here, right? Because that is where they will be my caps, right? Because cap needs to be there to actually stop the vertical movement of the hydrocarbon. And these type of reservoirs, when I see one hydrocarbon column above another hydrocarbon column, so H1, H2, H1, then H2, then H3, of course, and this is what we call as stacked reservoir. Okay, stacked reservoir. One reservoir is stacked above another. Of course, I can have hydrocarbon, you know, here as well. So this could be another trap. Okay? This anticline could also be another trap. So easier. So from that simple subsurface image, as you can see, we have kind of identified where the traps will be, where the spill points will be, how the structure is, where the unconformity is. I have drawn these reflectors, okay? So this is the thing that I have just done with this image is essentially called seismic interpretation. Is to interpret the seismic. Okay. Now, Let us say there is another thing we can do. Of course, this is my horizontal distance, and this is my vertical distance, right? Depth. Now, a seismic image can be expressed in the depth domain. This is in the depth domain, or it can be expressed in the time domain as well. You remember what we have been essentially in the last picture. If you go, so what I have been talking about, that these are T1 and T2, and these are we call as two-way times, because it goes once and then it comes back. Hence, T1 or T2 will be called as TWTs, or two-way time. Okay. So I can actually also have an image of seismic similar here, where you know other than depth, I can actually plot TWT. Two-way time can be plotted here as well. Then you actually do something called depth conversion. So if I have a time domain image, I do something called depth conversion. You do something called depth conversion to actually get a depth domain image. Okay, depth domain image. And to actually convert a time domain image to a depth domain image, we need something called a velocity model. What is velocity model? Velocity model is nothing but the distribution of velocity, against depth. How at each depth this velocity is essentially changing. Now, so this is one part of the seismic interpretation. The other thing that you do in seismic interpretation is, let me just try to explain that. Uh, the other thing that you do in seismic interpretation is, suppose you know uh, this is the reflector that I am interested in. Okay, let me just, yeah, this is the reflector I am interested in. Let me just get rid of the other things so that you can have a fresh start. Just a moment. Yeah. Let us say it's a depth domain image. So this vertical axis is depth, and then suppose I have a depth scale associated with it. This is a 100 meter, 200 meter, 300 meter, 400 meter, okay, so on and so forth. For example, I want to actually image this reflector, okay, this particular reflector, and I want to make a top structure map out of it. Okay, so from this seismic image, what I want to make, I want to make a top structure map. Please pay attention because this is an exercise that you will have to do soon. Okay? So this is a top structure map that I have to create. Okay? So what I do essentially, uh, suppose this is the map. This is map means this is the map view. Map view means I am looking. So this is my top surface, right? This is my top surface. So I'm looking at the top surface from the top. Okay. So I'm looking at this surface where I have, say, for example, a tree. I'm looking it from the top. Okay. And say the orientation of this, say the orientation of this line is say 110 degrees. 110 degrees. Okay. The orientation of this the line. What does that mean? Suppose this is then this is north. So 110 degrees means this is 90, say, suppose 110. And this is point A, this is point B. Point A, this is point B. Okay. And suppose this particular reflector that we are interested in, suppose this is called top B. Okay. I just named this reflector as top B. So what I will do, I will essentially, while I go from A to B, I will physically count the depth of this top reflector, top B, okay, from the surface. Okay. So at this at the very close to A, suppose, so I do that in a regular interval, and closer my interval, I will have a better result. Okay. Closer my interval, I will have a better result. But of course, you can imagine, if I become closer, if these points are closer, then it will take also more time, right? So at the very close, so and then these points are essentially given here. The vertical projection of these points on the AB line, right? This is the vertical projection of these points on the AB line. And then I simply write the depth value. So it changes from, this is 200 and, 200. Then suppose it becomes 210, 220, 250, 300. Of course, then it becomes again, becomes smaller, 250, 210, and then again 200, and so on and so forth. It can continue all the way up to it. So I got along these 2D points, along these 2D lines, what are the different depths at which I can interpret this? I can interpret this particular top B surface, right? Top B reflector. And then suppose I have one 2D line, then I have another 2D line. Okay, sorry. I have I have I have another 2D line. Okay, say suppose this is CD. Then I have another 2D line, EF, DH, okay, IJ. Generally, they could be equally spaced, but they might not be equally spaced. And then at each point, I have different depth values. Okay, depth values for this top B reflected. Okay, at each of these 2D lines. Okay, and then I will also have the, you know, the cross lines which are perpendicular to the inlines or at a very high angle to the inlines. Okay, and then on that also at each point I can measure the depth of top B surface with different depth values, right? And then what I can do, I can contour these depths. Contour. If I do contour of depth, what I will observe that perhaps I have an, you know, let me use another color. I can contour this depth and I'll perhaps observe that this is how the structure looks like, where this is the crest of this anticline, the crest of this anticline, and 3D, it looks like this. And perhaps, you know, this is my another color. This is my spill point. So spill point will is also at a depth, right? So that depth may be encountered here, okay, at this depth, okay, with respect to the top structure. So I can essentially plot the spill point here, or the spill point is nothing but my free water level. Okay? And anything above the free water level is essentially my hydrocarbon, right? So this is where my hydrocarbon is in the top structure map. And below the hydrocarbon, of course, is my water. Here is my water within this top structure. Here is my water. So if I, you know, try to draw it once more here, here is my top structure map of top B. And then, of course, I have depth contours. And these depth contours I have generated by interpolating. The depth contours I have generated by interpolating these different sections, right? Different cross sections. And then, okay, so suppose this is 200 meter, yeah, because you know, it is below the surface, so 200 meter means the crest. If you now compare that with the maps that you are exposed with, their higher value means, you know, elevation, and here lower value means actually elevation. You understand my point? Because here the reference frame is the top surface. So lower value means elevation, higher value means you are going at depth. But when the maps that you are exposed to in your structural geology class is like this. So higher value means elevation, but here lower value means elevation. So this is 200 meter, 300 meter, 400 meter, 500 meter. Okay. So this is the depth contour. Okay, and then I have found out that my free water level from the spill point analysis, the free water level is perhaps is at 400 meter. Okay. So here is my spill point that I have drawn for my free water level. So that what does that mean? That means anything below the free water level is water. Here is my water. and anything above the free water level is my hydrocarbon. This is hydrocarbon. Now I can simply calculate the area, right? I can calculate the area from the map above the free water level. Okay, so calculate the area. Next step is, after you create the top structure map, calculate area. Okay. And here I said that I have drilled a well. Okay, perhaps I have drilled a well here. Maybe the well is here. And then the well had a, for example, a gamma ray log, and you found a reservoir just beneath this top reservoir, perhaps you from this gamma ray, I have found out a reservoir which is perhaps has a thickness of 10 meters. So say the area, so the calculated area say is perhaps 100 square kilometer. That is what you have calculated from the top structure map. And then you have found the thickness of the reservoir. Remember, we are actually taking the gross thickness of the reservoir, because while we calculate STOIP, we are going to actually multiply net to gross with it. So we will take the gross thickness of the reservoir is say 10 meters. Okay. So GRV, what GRV stands for? Can you tell me? Anyone? What GRV stands for? Anyone? What GRV stands for?
Gross rock volume.
Gross rock volume. Excellent, Pratichi. So the gross rock volume will be then, did I remove it? Seems I have removed it. Doesn't matter. So the gross rock volume is equals to 100 kilometers square multiplied by 10 meters. So by analyzing the seismic, I have essentially calculated my gross rock volume. Okay. By plotting the depth of a particular reflector, along different inlines and cross lines, okay, over an area. I can calculate the area, and then I can calculate the reservoir thickness with the area, and then I can get my gross rock volume. And of course, while I calculate STOIP or GIP, yeah, first thing I need is GRV, and then but remember, when we talk about the thickness here, we are taking the gross thickness, not the net thickness. So gross GRV multiplied by net to gross multiplied by 1 minus SW multiplied by net to gross SW. What else? I have missed porosity, and of course the expansion factor. I'll get my STOIP, and similarly I'll get my GIP. Okay. So all these parameters, net to gross, saturation, porosity, I have calculated from my well logs, but the gross rock volume is calculated from seismic. Okay. So now let us look at few more seismics. Okay. So, and this is an interpreted seismic, as you can of course see, and here you can see, of course, also a 2D line. You can see the presence of a well, the real picture. Charboa 1, Ayer sub-basin. So the orientation of the 2D line is west northwest, east southeast. So if I now start putting that in a map, how would it look like? North, south, east, west, west northwest, east southeast. So the line is perhaps oriented like this, right? West, northwest, east, south. Okay. And then what I can observe, there are many different elements in this map. This is in this section. Okay, so you can see here, of course, first of all, this is the top surface itself has a slope. Okay, the top surface itself is not essentially flat. It's not like this. It has a slope. What is the reason? I don't exactly know, but could be anything. It could be also a slope of the sea. And then, of course, you can see uh, there is sedimentary rock. So this beautiful layer, beautiful stratigraphy being preserved here. And then after that, there is some hodgepodge type of seismic character, seismic reflection. So this is perhaps the igneous or the metamorphic basement. Okay, this is perhaps the metamorphic basement. Hence the beautiful character of the seismic layering is not observed. Okay, and then you can observe this basement is seriously faulted. Okay, so I can observe one fault, two faults, small fault, three faults, four faults, five faults, six, seven, eight, nine faults. Maybe another few smaller faults. So the basement is kind of faulted, and you will perhaps I'm sure you know by now that these are nothing but normal faults. Now let's test the how do my students remember. Okay, third year or fourth year or fifth year, tell me anyone, uh, anyone, what is the type of normal fault we are looking at, whether we are looking at here, whether we are looking at domino type normal fault or we are looking at horst and graben. Let's see, domino type normal fault or horst and graben. Pratichi, tell me. Jay, tell me whether we are looking at horst and graben or domino type normal fault in this example.
So can you show the slide once?
Huh?
So can you show the slide once?
Yeah,
So domino types.
domino type, because they are oriented in the same. I mean, they are dipping in the same direction, right? So perhaps there was a one unidirectional extension, if you remember, right? So of course, because of this faulting, these small basins have been created. These small basins have been created. These accommodation spaces have been created, and within that accommodation space, I have the formation of these whole sedimentary layers. Okay. And then these faults got reactivated. These faults got reactivated, and I see that it has also created faults. But in this case, they are horst and graben. You see, they are dipping in both the directions. Okay, they have created horst and graben on the sedimentary layer. Okay, there is another beautiful thing that you can observe here, that the sedimentary layers closer to the fault are thicker. Here, at least, the sedimentary layers closer to the fault is thicker. But as we move away from the fault, it becomes thinner, and this is what we called a growth strata. Okay, and another question again, let me ask my students, what does growth strata indicate? What type of deformation growth strata indicate? You remember I taught you about growth strata. Ratichi, tell me, Vangshika is there? Is Vangshika there? Okay, Aniket, tell me, what does growth strata indicate? What type of deformation?
Hello, sir.
What does growth strata indicate? What type of deformation do they indicate? Sin sedimentary deformation. You remember that when we talked that while deformation happens, if sedimentation also happens, it creates growth strata. You should remember that we talked and discussed about it in details. Okay. Anyway, so this is what we call as sin deformational sedimentation. Okay, sin tectonic sedimentation. So this refers to sin tectonic sedimentation. Okay. And now, of course, all these layers you can see, these uh, blue layer, these yellow layers, this orange layer, this red layer, they are all my, of course, top structures, right? Yeah, like we have drawn top A, top reservoir here. So maybe this is top A, this top B, and so on and so forth. Now, if I have, the gamma ray inscribed here, I should be able to find out. Of course, the gamma ray will not be there because this is water. Nothing will be there. So if I have my gamma ray, I should be able to find out where my sandstone is, where is shell, and something. And then I can multiply my. So if I do the same exercise, if I have multiple number of, in lines and cross lines like this one, okay, I can pick up any horizon, at all these lines and multiply, put their depth values in it. Yeah. Now look at this one here. You see, this is a time series seismic image. Yeah, because in the y-axis I have two-way time. I have to, before we do any interpretation, we have to convert it into depth. Okay, so that's why we will need a velocity model here. Right? And then we can do that picking of the top structure map, and then we can multiply the top structure map from the thickness that we observe from the gamma ray, and do that exercise. Okay, so we will continue with seismic interpretation with bit more slides in the next class, and we will start another new topic, of course, as well in the next class. If you have any question, please go ahead. Question. Class is awfully silent, which I don't like. Meenakshi, you have any question? Or was it clear? Okay. All right. If you don't have any question, then I stop the class here, and I will, see you on Monday. Thank you. And but I wish to get your assignments submitted as the date given, as per the date given. Thank you.